Greetings, everyone. Welcome to our immersive journey into the world of PVD basics, exclusively brought to you by Semi Slides. I'm your dedicated guide, Semi Sherpa, thrilled to accompany you on this enlightening expedition into the intricacies of physical vapor deposition, PVD, technology. Our diverse audience, be it experienced engineers, curious students, or pioneering professionals venturing into the semiconductor domain, will find this series to be a rich reservoir of knowledge, designed to foster a deep understanding of plasma technology's core concepts and expansive applications. Together, we will navigate through the complex currents of semiconductor processes encompassing PVD. Our voyage will encompass a variety of significant territories, including DC Magnetron Sputtering, Reactive Sputtering, Pulse DC Sputtering, Advanced Sputtering, and PVD target manufacturing. So, hold on tight as we prepare to plunge into the captivating cosmos of PVD basics, a cornerstone in the realm of semiconductor manufacturing. Fasten your intellectual seatbelts for a journey that promises to be as enlightening as it is exciting. Ready to embark? Let's delve in. The fabrication of semiconductor chips starts with a silicon wafer, the foundation for this complex procedure that entails up to about 1,000 steps. The journey from a blank silicon canvas to a finished chip is a series of repeating cycles, each involving a core set of steps. The first core step is material deposition, which involves layering various materials such as conductors, insulators, and semiconductors onto the silicon wafer. Each of these layers plays a critical role in the chip's function, with their individual properties being determined by the materials utilized. Following this is a group of steps known as the patterning process. This process integrates photolithography, dry etching, wet etching, ashing, and stripping into a streamlined sequence. Photolithography projects an integrated circuit layout onto the silicon wafer. The subsequent etching processes create desired patterns on the wafer by selectively removing layers, and ashing and stripping steps are conducted to remove any residual photoresist, ensuring the wafer's cleanliness for the next cycle. While not always required, an optional step in the fabrication process is ion implantation. This procedure, when needed, bombards the silicon wafer with ionized particles to adjust its conductivity. These core unit processes, from material deposition through to optional ion implantation, can be repeated in cycles, ranging from 40 to 100 times. Each cycle further refines and builds the network of electronic components on the silicon wafer, in accordance with the complexity of the chip design. The final product undergoes electrical die sorting, EDS, for inspection before heading to packaging. The role of thin film deposition is significant in the fabrication of a semiconductor chip, as it supplies the functional materials that form the fundamental units of the final product, including conductors, insulators, and gates. The precise and controlled nature of this process highlights the complexity and innovation of modern semiconductor technology. Among the diverse range of thin film deposition techniques such as physical vapor deposition, PVD, chemical vapor deposition, CVD, atomic layer deposition, ALD, electroplating, EP, and spin coating, the focus of our discussion is the sputtering method, specifically, magnetron sputtering. Initially, in the academic research phase, the direct current, DC, and radiofrequency, RF, sputtering deposition method was favorable due to its capacity to deposit a wide array of materials with high purity. This adaptability made it an excellent choice for material studies, contributing significantly to our understanding of various materials at the atomic level. However, as we navigate the landscape of semiconductor manufacturing, our focus shifts towards DC magnetron sputtering. Over time, the evolution of this technique has paralleled the miniaturization trend in semiconductor devices. As these devices have become smaller, the challenges in the step coverage and thickness control of deposited films have become more pronounced. Consequently, the use of DC magnetron sputtering in the semiconductor industry is gradually fading. Despite this fade-out, it's important to note that DC magnetron sputtering continues to play a vital role in certain deposition processes. Specifically, it remains a crucial technique for depositing films of materials like titanium nitride, TiN, tantalum nitride, TiN, copper, Cu, aluminum, Al, and cobalt, Co. These materials are of significant importance in the construction of a variety of semiconductor devices.
The process of DC magnetron sputtering is one of the essential procedures used in semiconductor fabrication. In this process, we make use of DC plasma to facilitate the sputtering process. Firstly, let's understand what a DC plasma is. DC plasma is formed by the ionization of gas atoms in a DC electric field, typically between a cathode and an anode. The cathode, often termed as the target, is the material that we wish to deposit on the substrate or wafer, and the anode is usually the chamber wall or grounded shield. The key to the sputtering process is the formation of a sheath at the target surface. As the DC voltage is applied, high-energy electrons are repelled, and ions are accelerated towards the target. Upon striking the target, these ions dislodge or sputter atoms from the target material, which then move and condense on the wafer, forming a thin film. Now, in DC magnetron sputtering, the word magnetron is crucial. A magnetic field is applied to the DC plasma, which increases the path length of the electrons, enhancing their probability to ionize the gas atoms. This magnetic field helps to confine the plasma close to the target surface, increasing the sputtering efficiency. Moreover, it allows the reduction of the distance between the target and the wafer, facilitating lower pressure operation. In a nutshell, DC magnetron sputtering takes advantage of DC plasma and magnetic fields to deposit thin layers of materials onto a substrate efficiently and at low pressure. This technique is widely used for the fabrication of semiconductor devices due to its high deposition rate, material utilization, and the ability to coat complex-shaped substrates. The direct current, DC, magnetron sputtering equipment is a cutting-edge technology, imbued with an array of advanced features that ensure both the precision and efficacy of the thin film deposition process. One of the pivotal elements within this setup is the target, usually a disc-shaped piece of the material designated for deposition. The target material, secured on a supported backing plate, facilitates an environment conducive to efficient cooling and mechanical strength. This cooling function is imperative in the sputtering process as it aids in preventing the target material from overheating, thereby affirming the process's stability. The magnet is another integral component within the equipment. Engineered to rotate and generate a magnetic field, it confines the plasma within the proximity of the target. This ingenious design fosters a better erosion profile, ensuring a uniform sputtering of the target material and boosting its usage efficiency by enhancing the ionization process, ultimately leading to a higher deposition rate. Inherent in the DC magnetron sputtering equipment is the vacuum pump system, a vital fixture within the assembly. This system usually consists of a dry pump, serving as a roughing or four-line pump, in tandem with a high vacuum pump, which can be either a cryopump or a turbomolecular pump. This design allows for the maintenance of a base pressure within the range of 10 to the -9 to -10 torr, creating the optimal environment for the sputtering process to occur. During the sputtering process, the working pressure is preserved within the millitorr range, aligning with the molecular flow regime. This careful calibration guarantees the sputtered atom's straight line trajectory from the target to the substrate, enhancing the resulting thin film's quality. The substrate, the site of thin film deposition, is precisely secured in position by an electrostatic chuck (ESC) with a clamp ring on it. This arrangement not only ensures a uniform distribution of the deposited material on the substrate but also safeguards the wafer bevel from deposition through the edge clamp ring's protective mechanism. Lastly, the shield is instrumental in averting unwanted deposition on the chamber walls and other parts of the equipment. By restricting the sputtered material solely to the substrate, it bolsters the process efficiency while also maintaining the cleanliness of the equipment. Applied Materials, as a globally recognized leader in semiconductor manufacturing, has championed the development of the innovative single wafer cluster tool. The single wafer cluster tool is essentially a modular system that conducts an array of deposition processes on individual silicon wafers. An essential feature of the single wafer cluster tool is its capacity to seamlessly integrate numerous processing steps. This integration markedly reduces wafer handling and the accompanying risks, while improving process control, uniformity, and repeatability. The tool also manages to boost throughput by operating multiple process modules simultaneously, thereby expediting the thin film deposition process. As we delve into the following video, we'll have the opportunity to scrutinize the unique wafer routing process and Applied Materials cluster tool.
Applied's integrated copper barrier seed solution on the proven Endura platform is the gold standard for interconnect metallization in logic and memory fabs today. We integrate multiple surface preparations, film deposition, and metrology technologies on a single platform under vacuum. The process of filling copper interconnects begins with multi-chamber surface engineering. This preparation differentiates the materials and is key to achieving selective deposition. The surface preparation is followed by an atomic layer deposition, or ALD process, of a tantalum-based material that coats only the desired surfaces. Integrated onboard metrology is used to measure the accuracy of the deposited thin films without breaking vacuum. ALD deposition is followed by a densification process that improves the film's barrier properties. A thin CVD cobalt liner encapsulates the copper wires, extending circuit life and enabling copper reflow. Finally, highly directional PVD deposits a thin layer of continuous copper. Our unique system enables cold deposition and high-temperature processing in the same chamber. In summary, we integrate 7 consecutive steps in one system under pristine vacuum conditions to achieve void-free interconnects that deliver world-class electrical performance.
Applied Materials, a renowned leader in semiconductor manufacturing, has developed an innovative solution known as the Endura System, specifically for the physical vapor deposition (PVD) process. This comprehensive system has earned the nickname of a two-cluster system, owing to its dual wafer handling robots. This sophisticated system is divided into several crucial parts, each playing a significant role in the thin film deposition process. The load lock is the first point of interaction for the wafers. This unit forms a rough vacuum before the process begins, holds the wafers during the process, and vents the chamber back to atmospheric pressure once the process is completed. It's essentially the gateway to the Endura system, facilitating the transition of the wafers in and out of the system. Next is the dégâts chamber, whose primary task is to heat the wafer under vacuum conditions. This heat treatment serves to desorb any adsorbed gases from the wafer surface, ensuring a clean surface ready for deposition. Furthermore, the dégâts chamber also aligns the wafer, priming it for the upcoming process. The transfer module, TM, is essentially the heart of the system. It's responsible for transporting wafers between various chambers, ensuring an efficient and orderly process flow within the system. Then, the process module, PM, is where the real action happens. It's the actual process chamber where the PVD deposition process occurs. Every wafer is brought here for the deposition process, marking the crux of the system. An essential aspect of the Endura system is its vacuum management. Each module operates under a different vacuum level, ensuring optimal conditions for the task at hand. The PVD PM, where deposition occurs, operates under the lowest vacuum level. This meticulous vacuum management is vital to maintain a contamination-free process environment. The system is specifically designed to prevent potential contamination from harmful chemicals used in CVD or etch process modules. This safeguard is achieved by maintaining a higher pressure in the TM, thereby preventing any backflow when a wafer is inserted or removed from the TM to the PM. Moreover, the Endura system employs the Centura backbone, which features chemical-resistant and heat-resistant components. This addition further bolsters the system's reliability and performance. Ultimately, from the base pressure being progressively lower from the load lock to the PVD module to prevent surface contamination, every facet of the Endura system is meticulously engineered to maximize efficiency and precision in PVD processes. Target erosion is a key aspect to consider in the use and maintenance of PVD, physical vapor deposition, targets. Erosion is the gradual removal of material from the target during the sputtering process due to the bombardment by energetic ions, which are often argon ions. In the context of magnetron sputtering, a magnetic field is used to enhance the argon ion flux, making the sputtering process more effective. This is achieved through a phenomenon known as E-cross-B drift, where charged particles move perpendicularly to both electric, E, and magnetic, B, fields. The design of the magnetic field is crucial in achieving uniform target erosion. The field design can be shaped in various ways, such as a rotating design, a heart-shaped design, a spiral design, or Applied Materials' patented universal magnet motion, UMM. These designs ensure that the ion bombardment is evenly distributed across the target, preventing any specific area from being eroded excessively, thus maximizing the target's lifespan. However, care must be taken to avoid over-erosion. Overuse of the target can lead to the exposure of the copper backing plate, which can result in contamination and the generation of unwanted particles. Hence, it is crucial to monitor target erosion to ensure that it is maintained at an optimal level, allowing for efficient sputtering while avoiding undesirable side effects such as contamination. The physical vapor deposition, PVD, process, a key technique utilized in semiconductor manufacturing, sometimes encounters issues related to nodule formation. These nodules, essentially minute-raised points or clusters, originate from particles and can contribute to a phenomenon known as arcing, which results in additional particle generation and consequently, more nodules. Understanding the genesis and propagation of nodules is crucial in mitigating their impact. A single particle can lead to the formation of a single nodule, which may trigger arcing. Arcing is an undesirable event where a localized discharge of current occurs, causing physical damage and contamination. This, in turn, results in the generation of many particles, leading to the formation of many nodules and, subsequently, many instances of arcing. This cycle continues, compounding the problems associated with nodule formation. The prevalence of this issue is especially high in the processing of soft materials such as indium tin oxide, ITO, or germanium antimony tellurium, GESBTE. These materials have a propensity to generate particles during the PVD process. The etch rate of the particles tends to be lower than the etch rate of the target material. This discrepancy in etch rates can result in the particles remaining even after the sputtering process, contributing further to the nodule issue. Hence, controlling the generation of particles and effectively managing them is an essential aspect of improving the overall efficiency and yield of the PVD process. A significant challenge that arises during PVD process is edge symmetry issues, due to asymmetries at the wafer edge. These issues are brought on by what are known as line-of-sight behaviors, where the thickness of the deposited thin film on the sidewall of the wafer becomes increasingly non-uniform as it nears the wafer edge. Overlay marks, which are often used to align layers in the photolithography process, typically feature a step structure. This structure is symmetrical at the center of the wafer, but as it extends towards the edge, it becomes asymmetrical, leading to a wafer scale term. The asymmetry issue can result in non-uniform overlay errors, and if not addressed, these errors can cause pattern misalignment on the wafer. One must also note that even if the photolithography process goes as planned in terms of overlay, in the after-develop inspection or ADI state, significant scale term errors can still be observed in the actual pattern after the etching process, in the after-etch inspection or ACI state. Hence, measuring the in-cell overlay and providing feedback to the photolithography process is critical in ensuring proper pattern alignment. This process, known as MRC, misreading correction, can help minimize the impact of edge symmetry issues on pattern alignment.
Physical vapor deposition, PVD, processes, crucial for semiconductor manufacturing, can often involve a method known as reactive sputtering. Reactive sputtering typically entails the use of a target material in a gaseous environment, with the gas becoming reactive under specific conditions, leading to the formation of a compound material on the substrate. Take, for example, the production of titanium nitride, TIN, films, which can be achieved through two primary methods. The first involves using a TIN target in an argon sputtering environment. However, this approach faces several challenges. Creating the TIN target can be complex and difficult, and the resulting target often exhibits high resistance. Furthermore, the sputtering yield of TIN is relatively low, and the combined use of titanium, Ti, and TIN is impracticable due to issues related to vacuum levels and power control. An alternative, and often more beneficial approach, is to utilize a Ti target in a nitrogen, N2, reactive sputtering environment. This method allows the Ti atom sputtered from the target to react with the nitrogen in the plasma, forming TIN on the wafer. The creation of a Ti target is relatively straightforward, generally achieved through milling, and the resulting target exhibits lower resistance. Furthermore, the sputtering yield of Ti is higher, making this process more efficient. Importantly, this method allows the deposition of both Ti and TIN films in a single chamber, thereby expanding its utility. In this context, Ti can act as a glue layer, enhancing the adhesion between the TIN layer and the substrate, and it can also play the role of a crystallinity booster, improving the structural quality of the deposited film. This method also has the advantage of improved vacuum levels, and it potentially offers an improvement in particle management. Target poisoning is a significant phenomenon in physical vapor deposition, PVD, processes, particularly in reactive sputtering methods. Understanding and managing target poisoning is crucial for ensuring the quality of the deposited film and the efficiency of the process. In reactive sputtering, the term target poisoning refers to the condition in which the sputtering target surface becomes covered by the reactive gas in the chamber, for instance, nitrogen, N2, in the case of titanium nitride, TIN deposition. The state of the target surface can alternate between a metal mode, where the surface is mainly titanium, Ti, and a compound mode, where the surface is primarily composed of the compound Tin. The transition between these modes often involves a hysteresis behavior, which means the path of change is different depending on whether the transition is from metal mode to compound mode or vice versa. Optimizing the N2 flow is essential to balance between achieving a high deposition rate and maximizing film nitridation. However, target poisoning can result in the variable composition ratio of titanium over nitrogen, both from wafer to wafer and within a wafer. This fluctuation can lead to inconsistencies in the properties of the deposited film, which is often a challenge in semiconductor manufacturing processes. Additionally, the transition from the seed, initial, layer to the bulk, main, layer can be affected, further complicating process control. The benefits of operating in the target poisoned, compound, mode include a higher deposition rate and a reduction in arcing incidence. However, there are drawbacks. In the case of reactive sputtering of tantalum Ta with N2, for example, excessive N2 flow in the compound mode can cause the film to transition from an amorphous state to a polycrystalline state, thus degrading the barrier characteristics, which are often critical in applications such as advanced microelectronic devices. DC Magnetron Sputtering, despite its significant contributions to thin film deposition, inevitably has its limitations, especially when dealing with insulator targets and reactive sputtering using oxygen. Let's delve into these complexities for a more comprehensive understanding. The use of insulator materials as targets in DC magnetron sputtering poses a considerable challenge. The key to a stable DC plasma lies in the existence of a conductive target surface. DC plasma harnesses the voltage difference between the cathode and anode, inciting ionization reactions that in turn generate plasma. To uphold a current, the material in use needs to possess conductive properties. Essentially, conductive materials permit the movement of electric charge, thereby facilitating the direct current flow. On the other hand, insulator or nonconductive materials do not support the easy flow of electric charge. Consequently, a direct current cannot permeate through, making it a challenge to uphold the necessary ionization for plasma creation in DC plasma systems. This explains why DC plasma is typically employed where the target material exhibits conductivity. Charge accumulation over time is a characteristic of insulating materials, which can lead to voltage fluctuations and process instability. In extreme cases, this could escalate to arcing, a condition where the built-up charge discharges all at once, potentially leading to damage to both the target and substrate. Turning our attention now to reactive sputtering with oxygen. In this process, a reactive gas, such as oxygen or nitrogen, is introduced into the sputtering chamber. This gas undergoes reaction with the sputtered material particles, leading to the formation of compounds that subsequently condense onto the substrate. However, using oxygen presents its unique challenge, known as target poisoning. The sputtered material undergoes a reaction with oxygen, culminating in the formation of a thin insulating layer on the target surface. This layer not only interferes with the sputtering process but can also prompt localized oxidation of target materials and the deposited thin film, which in turn can lead to arcing issues. Pulsed DC sputtering is a notable variation of the conventional sputtering process, typically employed in physical vapor deposition (PVD) methods. It becomes particularly beneficial when dealing with high resistance or soft target materials such as germanium antimony telluride (GST), carbon, or indium tin oxide (ITO). Instead of using a continuous direct current (DC) as in traditional sputtering, pulsed DC sputtering utilizes an asymmetric bipolar pulsed DC waveform. This means that the voltage applied to the sputtering target alternates between positive and negative at a high frequency, typically in the range of tens of kilohertz to a few megahertz. The process works by applying a negative voltage to the target for a majority of the duty cycle, during which the sputtering of the target material occurs. Then, for a short period, a positive voltage is applied. This creates a flux of fast electrons that move towards the target, neutralizing the charge buildup on its surface. This cycle of sputtering during the negative voltage phase and surface discharging during the positive voltage phase repeats at high frequency. One of the significant advantages of pulsed DC sputtering is its capability to suppress arcing. The detrimental effects of arcing become particularly notable in sputtering high resistance or soft materials, where it can cause the emission of macroparticles or droplets that degrade the film quality. However, there is a trade-off in pulsed DC sputtering. While it mitigates arcing, it tends to decrease the deposition rate compared to conventional DC sputtering. This slower deposition rate could potentially increase process times or reduce throughput, which can be a significant consideration in high-volume manufacturing environments.
In the physical vapor deposition (PVD) process, collimated directional sputtering (CDS), or simply collimator PVD, is a unique technique that utilizes a structure known as a collimator to optimize the particle flux during deposition. The collimator is typically a honeycomb-shaped structure that is placed between the PVD target and the substrate. The primary role of the collimator is to enhance the directionality of the sputtered particles. It does this by allowing only the particles moving in a direction perpendicular to the substrate to pass through. This enhanced directionality significantly improves step coverage on the substrate, making collimator PVD an excellent choice for applications requiring conformal coatings on substrates with complex topographies. However, the use of a collimator also presents certain challenges. One key trade-off is the decrease in deposition rate, as the collimator restricts the number of particles reaching the substrate. To counteract this, systems may employ time or power correction mechanisms that adjust the deposition process parameters to achieve the desired coating characteristics. Additionally, the collimator technique has limitations when used for applications requiring thick coatings. The collimator itself can become a source of particulate contamination due to temperature fluctuations and the need for frequent replacement, which leads to shorter preventive maintenance (PM) cycles. This is an important consideration in the overall cost and efficiency of the PVD process. Long throw sputtering (LTS), a particular method in physical vapor deposition (PVD), makes use of a significantly increased distance between the target and the substrate. This method gives the sputtered particles a longer mean free path (MFP), which inherently leads to an improvement in the directionality of the particles. The advantage of this setup lies in its potential to enhance step coverage, particularly useful in the manufacturing processes where high aspect ratio features are present. However, the long throw sputtering technique does come with its set of challenges. One primary issue relates to the asymmetry at the wafer edge, leading to possible misalignment. This is due to the fact that particles being sputtered from the target have more space to diffuse and deviate from a straight trajectory before reaching the substrate. In long throw sputtering (LTS), the deposition rate is typically lower than that in conventional sputtering. The fundamental reason lies in the larger throw distance, the space between the target and the substrate. As this distance increases, the sputtered atoms have a higher probability of colliding with the chamber walls and other internal structures. These stray particles adhere to the chamber surfaces, consequently reducing the number that reach the substrate. Thus, due to this increased particle loss, the deposition efficiency decreases, resulting in a lower overall deposition rate. Furthermore, the uniformity of the film deposited by LTS may be compromised due to the longer throw distance. This is an important parameter to consider, as film uniformity directly affects device performance in many applications. Lastly, LTS systems may experience shorter preventive maintenance (PM) cycles, indicating a higher frequency of maintenance and potential downtime. Ionized physical vapor deposition (i-PVD) represents a sophisticated evolution in PVD technology, leveraging ionization to augment deposition attributes. The ionization enhanced directionality is particularly beneficial for high aspect ratio structures and more intricate geometries. Conventional PVD techniques may struggle to provide a uniform and high-quality coating for such structures, but with the ionization process in i-PVD, we can achieve superior results. One notable variation, ion metal plasma (IMP), utilizes an RF coil to ionize sputtered particles, thus improving the energy and directionality of the deposition process, enhancing the coating precision and quality. Still, this process isn't without challenges. The RF coil presence within the deposition chamber risks particle generation, potentially leading to defects in the deposited film. To mitigate this risk, self-ionized PVD (SiP) has been developed, eliminating the RF coil from the chamber and reducing particle generation. Instead, a new magnet design within the chamber is introduced to replicate the ionization effect. However, carefully managing the wafer's applied bias during the process is critical, as an excessively high bias can lead to resputtering, thus impacting the overall deposition rate and the film's consistency. Lastly, ENCO-RE, enhanced coverage with resputtering, another i-PVD variant, aims to further optimize the deposition process. It uses a tantalum coil for barrier layer deposition, typically adopting a two-step process to improve the conformality of the tantalum film. This method balances the need for high coverage with the ability to fine-tune the deposition process, resulting in a conformal barrier layer, which is critical for complex semiconductor device structures. To summarize, ionized PVD techniques like IMP, SIP, and NCO represent significant advancements in plasma technology. Each offers unique solutions to challenges in thin film deposition, enabling better control, precision, and efficiency in semiconductor manufacturing processes. These techniques are essential to meet the growing demand for ever more intricate and miniaturized semiconductor devices. Off-axis deposition is a unique technique used within the physical vapor deposition (PVD) process. Its name is derived from the position of the substrate relative to the target material, where the substrate is placed off the direct line of sight from the target. This configuration results in a low-energy and low-damage process, ideal for sensitive materials or structures that require gentle deposition techniques. The cluster tool used in off-axis deposition facilitates the coating of materials by utilizing multiple targets. It does so without causing high-energy impacts or any significant structural damage to the delicate substrate. While this process exhibits several advantages, it is worth noting that it comes with a trade-off, as off-axis deposition generally presents a lower deposition rate compared to standard PVD techniques. This means that the overall process time may be increased, impacting the efficiency and throughput of the fabrication operation. Interestingly, the off-axis configuration can be advantageous for achieving excellent uniformity across larger substrates. As an example, a 4-inch target can provide uniform coating on a 12-inch wafer. This is particularly beneficial in industries such as semiconductor manufacturing where large wafers are commonplace. Off-axis deposition plays a crucial role in the production of magnetoresistive random access memory (MRAM), where the magnetic tunnel junction (MTJ) stack deposition is required with high precision. The process demands stringent control over the thickness of the deposited layers, down to 0.1 angstrom. Furthermore, off-axis deposition allows for co-sputtering, where two or more materials are sputtered simultaneously onto the substrate. This can be achieved using both RF and DC plasma sources, providing additional flexibility in the materials and structures that can be created. Finally, a multi-target system can be used in off-axis deposition. The use of shutters and shields allows for precise control over where and when the materials are deposited, helping to prevent unwanted deposition and ensuring the quality of the final product.
In physical vapor deposition (PVD) processes, one of the core components that come to the forefront is the sputtering target. Often referred to simply as the target, this consumable item takes the form of a high-purity metal disc and serves as the primary source material for the metallic film that is deposited during sputtering. To ensure optimal performance, the target material must be of electronic grade, that is, exhibiting a purity greater than 5 nines, or 99.999%. Targets used for non-magnetic materials are sometimes processed as monolithic entities, meaning they are formed as a single piece without the need for a backing plate. The target is not standalone in its operation, it interfaces closely with other components in its assembly, such as the backing plate. This backing plate is a crucial constituent that performs several roles. The backing plate is typically composed of a copper-chromium alloy, Cu/Cr, chosen for its excellent thermal conductivity which aids in the cooling of the target during operation. It also functions as an electrical conductor, serving as the cathode in the sputtering process. The backing plate is often made from oxygen-free steel to prevent deformation at high temperatures. The bonding between the target and backing plate is another significant aspect. This bonding ensures efficient heat transfer and mechanical integrity. Part of the assembly also includes a particle trap surface to catch any stray particles during the sputtering process, thus maintaining the cleanliness and integrity of the sputtered film. Additional structural features include an O-ring groove and bolt holes, designed for sealing and mounting purposes respectively. With all these integrated features, the target structure and PVD processes not only acts as a source of depositing material but also contributes to maintaining the overall process efficiency and reliability. The casting or melting process in manufacturing physical vapor deposition (PVD) targets involves several intricate steps, each one carefully designed to ensure the highest quality of the target material. The initial phase of this process involves refining. The primary objective of refining is to control impurities in the target material. There are different refining methods utilized based on the inherent characteristics of the metal in question. Electrolytic refining is often used for copper, leveraging the principles of electrodeposition. In contrast, chemical refining capitalizes on the different solubility of elements in a given solution, and pyrometallurgical refining relies on different boiling points of substances. Generally, a combination of these techniques is used to achieve a high purity level of 5.9 to 6.9. Following refining, the melting and cooling process begins. This phase involves the production of an ingot. Vacuum induction melting, VIM, is commonly used at this stage. VIM has the advantage of being able to remove gaseous impurities such as carbon, oxygen, nitrogen, and sulfur, which are detrimental to the performance of the sputtering target. Once the ingot is prepared, it undergoes forming, involving forging and rolling processes. These processes serve to improve the mechanical strength of the target. Control over the target structure is crucial here, specifically, the grain size and orientation, as these parameters significantly influence the sputtering characteristics and performance of the target. Heat treatment follows to eliminate residual stress and improve ductility, further enhancing the mechanical properties of the target. Lastly, in some cases, electron beam, EB, melting might be employed. EB melting uses a focused beam of electrons to melt the material, offering high levels of control, and it is particularly beneficial for refractory metals and alloys. This process further ensures the homogeneity and purity of the sputtering target, ultimately leading to better thin film quality. The manufacture of PVD targets involves a crucial step known as target bonding, which is the union of the blank and the backing plate. This step is essential for the stability and integrity of the final target. The bonding procedure typically employs solder materials, with solder bonding or indium bonding being a commonly used approach. This method is widely applicable to many materials and is less susceptible to heat-induced alterations during the bonding process. A significant advantage of solder bonding is that it allows for the reuse of the backing plate, resulting in cost efficiencies. However, solder bonding does present certain limitations, such as a lower bonding strength, making it less suitable for high-power applications. Additionally, it is not suitable for operations at high temperatures, as the solder material, indium, melts at 156 degrees Celsius. Following the bonding process, the next step involves machining the target into the desired shape. This step typically involves techniques such as computer numerical control, CNC, machining and lathe work. A crucial aspect of this phase is the surface treatment of the target, which aims to control the presence of particles, ensuring a clean and smooth target surface. The final step in the target bonding process is cleaning and packing. The cleaning process aims to remove any cutting oil residue left over from the machining process, ensuring the target's cleanliness. Packing, meanwhile, serves to protect the product during transit and storage, ensuring the target's integrity is maintained until it is ready for use. The physical vapor deposition (PVD) market, characterized by a compound annual growth rate (CAGR) of 5.8%, has been influenced by a range of factors over the years. While traditionally the PVD process has seen extensive use in industries such as electronics, automotive, and medical devices, shifts in technology and industry trends have begun to alter its position. With respect to the semiconductor industry, advancements have led to certain segments gradually shifting away from traditional PVD techniques. Yet, it remains an essential technology in specific areas where its benefits are unique and indispensable. Key contributors in the PVD market include well-established companies. Honeywell, JX, and Tosho, for instance, are recognized for their production of PVD targets. The quality of these source materials is crucial for ensuring optimal performance of the resulting PVD coatings. Simultaneously, PVD equipment manufacturers like Applied Materials, Ulvac, TEL, and Canon and Ilva continue to play a significant role in the market. These companies produce the machinery used in the PVD process, with machine performance and capabilities playing a fundamental part in the efficiency of the deposition process and the quality of the end product. Overall, the PVD market continues to present a complex and varied landscape. While changing industry needs and advancing technologies have influenced its role, it remains a key process in areas where its unique capabilities are required. We greatly value your participation in this insightful journey through the essentials of PVD, a crucial pillar of semiconductor technology. Your dedication to learning and your relentless curiosity are truly commendable. Show your commitment to this shared quest for knowledge by giving a thumbs up, subscribing to our channel, and turning on notifications to stay abreast of our latest offerings. In the forthcoming episode, we'll venture deeper into the realm of chemical vapor deposition, CVD, and atomic layer deposition, ALD. Our exploration will illuminate the intricate details of these processes and their role in semiconductor manufacturing, providing essential insights into an array of deposition techniques that shape productivity and quality standards in the industry. Your continued support and unbridled enthusiasm are our driving forces. So, stay connected with Semi Slides as we persist in demystifying the complex world of semiconductor technology.